Hi friends, welcome to our channel. In this session, we will discuss contiguous memory allocation. Suppose a process that wants to execute that must be in the main memory. The process must be in the main memory. Main memory has to accommodate space. Assume this is the main memory. This is the main memory. The main memory has to accommodate both operating system and user process. Both the operating system and user process. Suppose in this main memory, that main memory is divided into two partitions. The first point is before allocation, how we are dividing the main memory. Generally, this main memory is divided into two partitions. One partition is for operating system, one partition for operating system, another partition for user process. Another partition is for user process, that is the process that we want to execute. This is the way we are dividing main memory. After that, contiguous memory allocation means the name specifies contiguous means sequential. Sequentially we are allocating the memory. Suppose if a process comes, that process brings one section of the memory that is contiguous to the next process, that is all the process, the memory is allocated sequentially. Now we will discuss in memory allocation we have two ways. We have two ways of memory allocation. First one is fixed sized partition. Second one, variable sized partition. Second one is variable partition. In these two ways we are allocating memory. This is memory allocation. So first move to fixed sized partition. Here the total available memory, ignore operating system memory. We are concentrating only on user process memory. Here the total available memory is divided into partitions of fixed size. Fixed size means the size of each partition is same. For example, this is the memory. This is the user process memory. For example, assume the size of this memory is some 500 MB. 500 bytes. Assume the size of this memory is some 500 bytes. Now my memory is divided into fixed partitions. That is the size of this one is 100, 100. This is the way I am dividing my memory. Whenever a process comes, what we will do, whenever process enters into the system, that process is placed into the input queue. The process is placed into the input queue. First, whenever a process requests for the CPU, for that process we are allocating one partition. For example, process P1 enters into the system. It requires some memory. What we will do? Assign this partition. Suppose the process P2 enters into the system. It requires some memory. In the similar way, suppose the process P3. Whenever a process enters into the system, we are allocating one block of memory to that particular process. One block of memory to that particular process. For example, if process size is some 80. Process size is only some 80 bytes, but the partition size is 100 bytes. What we will do? Even though the size is smaller than the available size, we are allocating complete 100 bytes to the process. You got the point? Whatever the size, we are definitely allocating 100 bytes of memory to that particular process. For example, if process size is some 120, what happened? For this process, we have no memory is available. For this process, no memory is allocated. This is the way we are assigning memory to the process. Whenever a process terminates, what happens? Whenever a process terminates, that is completes its execution, completes its execution, this memory is makes available. This is the memory, this is the free memory. This memory is makes available for the next process. Available for the next process. This is a fixed sized partition. Here how many number of process at a time runs? Simply depends on the number of partitions. For example, this contains 5 partitions. We are allocating a maximum of 5 process at a time. We are allocating a maximum of 5 process. Now come to variable partition. Here what is the concept? This is the main memory. Suppose this is the OS. This memory is allocated to different process. How? In this operating system, in variable partition, operating system maintains a table. It consists of 2 parts. What are the parts? Available memory and allocated memory. So operating system maintains a table which contains the index of available memory and allocated memory. Suppose if you are not understanding this ones, ignore. This is the complete memory available. Initially, this is the complete memory available for a process. Here no partition is done. In fixed sized partition, initially we are divide memory into different blocks. But in variable partition, no partition is done. The complete available memory initially called as whole. The meaning of whole means the large available free memory is called whole. Whenever a process enters into the system, all the processes are placed in input queue. By default, process enters into the system, the processes are placed in the input queue. First, operating system selects a process from the input queue. For example, process P1 is selected. What is the memory requirement for this process? Check the memory requirement for this process. For example, this process requires 100 bytes of memory. It checks the table whether 100 bytes of memory is available or not. So you got the question. First it picks a process and check whether the requirement memory is available or not. If the required memory is available, we are allocating that process. We are allocating this process and update the table. Update the table means the 100 bytes of memory available is decreased and it is added to allocated. So for example, first process P1 enters into the system. It occupies 100 bytes of memory. So assume initially we are assuming total 500 bytes. Suppose this user space again 500 bytes. Next process P2 enters into the system. For example, process P2 requires only some 70. We are allocating process P2. How much amount? This is 100. This is 70 only. Compared to previous one. In the previous one, first process 100, second process 70. Total 170. But in this method, we are allocating 200. But in this method, we are allocating only 100 plus 70. Very good. For example, next to process P3, it requires some 200. I am assigning 200. Next to process P4, suppose requirement of process P4 is 30. So how much completed? 300, 400. Only 100 bytes of memory is available. Assume if process P2 is deleted. Whenever a process is deleted, here it forms a hole. Whenever a process is deleted, it forms a hole. How much available memory? Now available memory is 170. This space is 100. That space is 70. Total available memory is 170. Okay. Whenever a process enters into the system, it checks the memory. Whether it is available, allocate the memory. Whether it is not available, simply wait in the input queue. Whenever a process terminates, its memory is freed. That is, it is added to available memory. Here we have some problem of fragmentation. At the end of this topic we will discuss a fragmentation. Okay, similar same diagram is placed here. So this is the variable size partition. Okay, you got the clear idea of fixed sized and variable size. Fixed size means we divide into partitions of fixed size. Variable means whenever a process comes, add into the free available space. Whenever it terminates, add to the operating system table. Okay. In this memory allocation, we are getting a problem. The problem is dynamic storage allocation. Dynamic storage allocation problem occurs. What is the problem? How we are dynamically allocates a process to the memory. Suppose I am requesting a memory of size n bytes. Suppose I am requesting a memory of size n. How you will satisfy your request? Okay, how we are satisfy your request? So for this dynamic storage allocation, we have three strategies. One is first to fit, best to fit, worst to fit. By using these three ways, we are dynamically allocating the process of our request. Okay, for example, this is the memory. After some insertions or deletions, the memory is divided of different sizes. Assume this is some 100, 50, some 200, 150, suppose 300, 250. These are sizes of each block. Assume these are the sizes of each block. First, follow the first fit approach. What is the first fit approach? Whenever a process requests for the memory, in the first fit, we are searching from the starting. Assume we are searching from the first free hole. If a first free hole is sufficient for that particular process, if the hole is sufficient for the process, we are allocating. Suppose my request, suppose a process of size 150. How we are allocating the memory? In the first fit approach, we are checking for a free hole that is big enough to store the process. First, P is checked. This size is 100. It is not suitable. This size is 50. It is not suitable. What is the size of this process? Here the block memory size is 200. Our 150 is stored in this position. So P is stored in, suppose the P1 is stored at this position. Assume P2, suppose size of P2 is some 200. Size of P2 is 200. Again search from starting position, or we have one more way. Always we search for the required memory from the starting position or search from previously stopped position. That is, we have to search from this position or from this position. Suppose I am searching from starting position. The size is 100. It is not sufficient. The free size is 50. These are the free sizes. The free size is 50, not sufficient. Here the size is 200. But it is already allocated. Even though the size is waste, it is already allocated. 150, not sufficient. 300. So we place process P2. This is the first fit approach. That is, we are searching where the first hole that is big enough to store the particular process. Observe, by observing, suppose if we have one more process P3 of size 300, where we are storing 300, that is where we will store P3. So the first fit approach is not suitable. Move to best fit approach. Suppose this is first. In the best fit approach, from the starting to ending we search. The best fit approach, from the starting memory free location to end free location we search where it exactly fits. That is the lowest possible requirement. For example, first process 150. The size is 100. not sufficient, 50 not sufficient, 200. Even though it is sufficient, scan the entire memory. So 150 and 150 exactly same. So process P1 is allocated. In the best fit, process P1 is allocated. Suppose if process size is 140, nearest to 140 is 150. So 150 is allocated. Next to process P2. So again start from the set. Process P2 is allocated in best fit. Process P3 also have same space. See this one? In the first fit, process P3 is not allocated, but by using best fit, process P3 is allocated. Okay, and move to worst fit. Worst fit means similar to best fit, exactly reverse. In best fit, we search the entire free memory locations that is best suitable is allocated. In this search entire location that is last suitable, that is the worst suitable location. For example, 150. First process 1 is allocated to the largest hole. So what is the largest hole? 300. So process P1 is allocated at this position. Process P2. Next one is P2. Size is 250. This is the worst position. Next P3. There is no available space. This is the way to allocate the memory. This is the problem of dynamic storage allocation. This dynamic storage allocation problem is solved by using any of these things. Remember, best fit, first fit, worst fit, all those are, there is no guarantee that which one is best. Depending on situations, in one situation first fit is better than best fit. You think that in this situation best fit is better, but depending on the situation first fit is better than best fit. And worst fit is always a maximum waste case. Okay, dynamic storage allocation problem. And okay, it's clear. And move to previous one. So what we will discuss in the fixed sized partition or variable sized partition. Suppose the partition size is 100 bytes. Partition size is 100 bytes. If my process size is only 70 bytes, what about remaining 30 bytes? What about remaining 30 bytes? That is called fragmentation. Fragmentation means simply wastage of memory. Fragmentation means wastage of memory. So here 30 bytes of memory is wasted. See the previous example. Even though the requirement is 70 bytes, but I am allocating 100 bytes. The 30 bytes of memory is wasted. We have two types of fragmentations. One is internal fragmentation. Second one is external fragmentation. So we know internal fragmentation. Internal fragmentation is this one. This is the internal fragmentation. Suppose the size is 100. The size is 100. Divided into fixed sized partition. Suppose I am allocating a process which of memory 90. What about this remaining 10 bytes? Suppose allocate a process of 70. Remaining 30 bytes, remaining 10 bytes. So it is waste. Internal. Internal means we are allocating the memory to this partition. I am allocating the memory. I am allocating this partition, but it wastes 10 bytes of memory. This is called internal fragmentation. But move to external fragmentation. This is the important one. What is external fragmentation? Suppose the available memory, suppose the required memory is available, but it is not contiguous. It is not contiguous. For example, I have a process of size 100. What we will do? So 100 is available, simply allocates. If I want to store a process of size 150, what we will do? Here the total available memory in this system is 70 plus 100, 170. I am required only 150, but it is not allocated because these 70 and 100 are not contiguous. This is called external fragmentation. So external fragmentation means the required memory is available, but the memory is not contiguous, that is the memory is not sequential, that is called external fragmentation. What we will do to overcome external fragmentation? One technique is compaction. One technique is compaction. Compaction means whenever a process terminates, that free memory is added to the already available memory. That free memory is added to already available memory. That means after performing compaction, what happens? P1, it is stored. This memory is added to this available block. P3 of size 200, P4 of size 30. This is the remaining 170. Okay. Compaction means all available holes. Hole means free memory is called hole. That is available memory is called hole. All holes are combined into a single large hole. That is compaction. Now my requirement is 150. I am allocating 150 in the 170. In this way I am overcoming external fragmentation. This is the contiguous memory allocation techniques.